Hello Math Humans, we're going to do 6.3b today. We're going to be talking about applications of vectors. So our objectives are that we're going to look at some different notation, we're going to find component forms of vectors, and then we're going to look for the resultant of multiple forces. Alrighty, so if I have a coordinate system and I have a little vector, we're going to give him some magnitude, okay? And we've talked about I can break my vector into component form x and y. So I'm going to show you how to put this into component form, and then I'm going to give you some words of advice. So if I do the cosine of theta, okay, cosine is x over the magnitude. If I solve for x, I'm going to get x is equal to magnitude cosine theta. Same thing if I set up the sine of theta, it's going to be y over the magnitude, then y is going to equal magnitude sine theta. Now this assumption is that I'm doing math on the x-axis. I could do math up here, right? And I could use this theta and I could get the same value, but my trig ratios are upside down or opposite if I'm doing math up here. So I'm going to tell you in my class, I only want you doing math on the x-axis, period, end of discussion. And then we'll talk about some flexibility in other areas, but I think if you are consistent with your math, it makes difficult math more easy. So you're only going to manage math sitting on the x-axis ever, period. Okay? So when you set up your vectors, you're going to always draw and label. And if you set it up like this on the x-axis, the x-coordinate is always going to be magnitude cosine, and the y-coordinate is always going to be magnitude sine. If you don't do that, then you have to do additional trig, and I guarantee you're going to make some mistakes. So then the vector form, the component form, is going to become magnitude cosine of theta and magnitude sine of theta. Okay? And so then that's going to be what our component form becomes. The resultant is still going to be the square root of the x component squared and the y component squared, because the math is the same. And if I do magnitude times the cosine of an angle, typically your calculator is going to be in degrees. I'm still going to get a number, but I just arrive at that number a little bit differently. Okay? Other things that we need to know. Sometimes you will see component form written in a different manner, and it's going to be written as, instead of x plus y, it's going to be written as I plus j. Notice that if I write my component form as I plus j, there are no brackets. So I is going to equal the x component, and j is going to equal the y component. So nothing has changed, it's just a slightly different type of notation. Okay? So we would write it as I plus j, no brackets, or we would write it as x plus y. And your book will do some problems using both formats. As you move into upper division math, sometimes we use I and j, and we talk about cool things like the projection of a vector, and we do it in often I and j format, but that's above the scope of our course. Alrighty, the other thing that we need to talk about before we start doing our example are angles, because you need to be very comfortable with your angles. So if I have a coordinate system and I'm talking about bearing, remember that north is equal to 0, and I always rotate to the right, period, end of discussion. I could also have a bearing that says maybe it is north 25 degrees east, and remember in that situation, I'm going to start at the first letter, I'm going to rotate, this is 25, and then 90 minus 25, can I do that math in my head? Probably not, because now I'm having a brain fart, so I'm going to get out my handy-dandy calculator. Whew, 90. Sorry, that's what happens when I haven't had enough coffee in the morning. And I can't even seem to push buttons this morning. Whew, so this is 65. We would do math down here. We would not do math up here on the 25, but that gets us in the right location. The other angle that is new for this particular section is called a direction angle. And a direction angle always starts at the x-axis. We're going to start on the x-axis and we're going to rotate counterclockwise. Okay, so you need to make sure that you understand the difference between all of those angles, because you will see all of these types of angles as we work with vectors. Bearing, we start at north, it's equal to 0. If they give you your bearing in this format, remember that we only do math on the x-axis. I will say that we only do math on the x-axis in my class because I think it is easier to manage. And then the direction angle starts at the x-axis and rotates counterclockwise. Alrighty, so I've got an example set up for us. So it says, find a component form of the velocity of an airplane descending at a speed of 150 miles per hour on a bearing of 250 degrees. So the first thing that I'm going to do is I'm going to draw a picture, because we should always draw pictures first. And the first thing that I'm going to manage is my bearing of 250. So if I start at north is equal to 0, 90, 180, 270, it's going to be 20 degrees shy. Okay, and then I'm going to have my x and my y. We're only going to do the math on the x-axis. Notice that x is going to be negative and so is y. Okay, we know that my magnitude is 150 degrees. So there's a couple of different ways that you can manage bearing, and I'm going to show you both, and then I'm going to show you my preference. So if you're using my method, and it's not really my method, it's just my preferred method, remember that we talked about in component form, if my reference angle is sitting on the x-axis, it's going to be magnitude cosine and magnitude sine. Okay, it's a G. So then for this vector, it's going to be, and I don't have to manage signs, so I'm going to write no signs in my method. Okay, and actually I lied, I do have to have signs. It's the other method that I don't. Whew. So in this one, if I look at this, I know that my x component is negative, and I'm going to do 150 cosine 20, and I'm going to do a negative 150 sine 20. Okay, and then I can push buttons on my calculator, and I would get that the component form is going to be a negative 140.954 and a negative 51.303. So in my method, I manage my signs myself, and I use the angle that's sitting on the x-axis. The other method, I don't know what to call them, but we'll just call it the other method, is going to manage the original angle, and that manages the signs itself. So it's going to be 150 cosine 250, and it's going to be 150 sine 250. Okay? You can't mix methods. So each method has its own advantages and disadvantages. In my experience, this method students seem to make less mistakes with. So now all I have to do is report my answer, and I'm going to write component form, and then there we go. So I do not care which method you use. I prefer that you use this method because we have just studied 2 chapters of trig, and we have been doing math on the x-axis, so I would like to be consistent. I'm okay if you use this method, but if you mix the 2 methods, you're in trouble. Alrighty, I have our second example already written. Ta-da! So example number 2 says an airplane is traveling at a speed of 500 miles per hour on a bearing of 330 degrees at a fixed altitude with negligible wind. This is relevant because that means that we have one less force to manage. When the plane reaches a certain point, it encounters a wind with velocity of 70 miles per hour on a bearing of north 45 degrees west. What is the resultant and direction of the plane? Alrighty, So I'm going to draw a diagram for each vector, okay? So I'm traveling on a bearing of 330. So 330 is all the way around, and it's 30 degrees shy of 360 because remember for bearing we start at north. Well, if this is 30, that means this is 60, and I have a negative x and a positive y. And there's my vector, make it a little bit darker, and this is going to be my plane, okay? When I reach a certain point, we don't know what that point is, I encounter some wind, and it's going at north 45 degrees west. So here's north 45 degrees west. This angle, the complementary angle, is 45. Again, I have a negative x and a positive y, okay? Alrighty? So now what I'm going to do is I'm going to just sketch these two vectors together. So if I had the first vector, here's my airplane, and then here's my wind. So this is the plane, this is the wind. The resultant is going to be over here in the second quadrant, which means that x is going to be negative and y is going to be positive. That helps me to kind of manage my math. So now what I'm going to do is I'm going to break each force down into its component form. The plane is going to be a negative x, magnitude is 500 miles per hour cosine 60, and a positive 500 sine 60. Okay. My wind is going to be 70 miles per hour, so it's a negative 70 cosine 45, and a positive 70 sine 45, okay? And then I want to find the resultant. So I'm going to add these together, and I'm going to add down, okay? So if I push buttons on my calculator, remember that my calculator is going to be in degrees, I'm going to get a negative 200.503 and 482.510. X is negative, y is positive, which confirms the second quadrant, okay? So my direction said, what's the resultant? So my resultant is here, but they want to find, when they ask for the resultant, they want the magnitude of the resultant. So I'm looking for the magnitude. Well, that's just going to equal the square root of the negative 200.503 squared plus 482.510 squared, and I get that my resultant is 522.511. We always have to include units, miles per hour. I'll report my answers in a little bit. Okay. My angle is here. I know an x and a y component, so I need to find the direction. So now I'm going to do trig to find that theta. So I'm going to say that the tangent of theta is y, 482.510, divided by the 200.503. You do not need the signs because we're just finding the measure of the angle. So theta is going to equal the inverse tangent of those two numbers, divided by the 200.503, and you get that theta is 67.435 degrees. And we've talked about this before when in Rome. So the problem started with a bearing of 330 degrees, so we're going to finish. So my bearing is going to equal 90, 180, 270 plus theta. So it's going to be 270 plus the 67.435 degrees, and my bearing is going to be 337.435 degrees. So now I'm going to report my answers in a concise location. So I'm going to say the magnitude is 522.511 miles per hour. You always have to include your units. And my bearing is going to equal 337.435 degrees. Okay, and then I would have finished the problem. So I think this is the easiest method of managing your vectors. You can do whatever you choose to do. I like this method best. All right, we have one more example. So we have three forces with magnitudes of 70, 40, and 60 acting on an object at angles of a negative 30, 45, and 135 respectively, which means that the negative 30 goes with the 70, the 45 goes with the 40, and the 135 and the 60 go together. Find the magnitude and resultant. So I'm going to split it up into component form, and I think I can get all three of these on the same diagram. So I have 70 pounds at a negative 30 degrees. So here's going to be my 70, and this is the 30, positive, negative. Then I'm going to have 40 pounds acting at 45 degrees. So here's my 40 pounds, and he's positive and positive. And then my 135 is over here. The complementary angle is going to be 45, negative, positive, and this one is my 60. Okay? So now I'm going to break them down into component form. Okay? So for vector number 1, I'm going to call this vector 1, vector 2, and vector 3. So vector 1, in its component form, is going to be 70 cosine 30. It's positive. And then I'm going to have a negative 70 sine 30. Vector number 2 is going to be magnitude cosine, oops, I forgot to write down my angle, 45, 45, and then sine is also positive, so 40 sine 45, okay? Vector number 3, over here in the third quadrant, the magnitude is 60. I have a negative x cosine 45 and a positive 60 sine 45. Okay, those are my three forces. To find the resultant, I'm going to add down, and I'm going to push lots of buttons on my calculator. When you do, you get 46.480 and 35.711. So this x and y are both positive, implies that my resultant is in the first quadrant. So let's add these together just to see what happens. So I'm going to start with my first one, and then here's my second one, and then here's the third one. Okay, kind of crappy math, but my resultant is going to be in the first quadrant. I think it's helpful just to add your vectors together so that you can see in theory if your resultant has the coordinates that you think it should have. So now I can find my magnitude. My magnitude is the square root of the 46.480 squared and the 35.711 squared. So I get that my resultant is 58.615. I'll report in a minute. Now I need to find my theta. So remember, theta is going to be right there. There's the x and y. So theta is going to equal the inverse tangent of y, 35.711, over x, 46.480. And when I do that math, I get 37.535 degrees. Okay? This one's asking for, I'm going to call it a direction angle because no bearing angles were given. And so remember that a direction angle starts at the x-axis and rotates counterclockwise. So this is going to be my direction. So now I'm going to report my answers nice and concise. So I'm going to say the magnitude is 58.615 pounds. And then, or you could write hashtag, but remember, hashtag actually meant pounds before it was a hashtag. That was its previous life. And theta, which is equal to the direction angle, is going to be 37.535 degrees. Alrighty, that's it for today. I think it's a very nice and polite version of vectors. I will see you soon.